Hello, everyone, and welcome to today's session about operationalizing machine learning. My name is Martin Stein, and I'm with Union. I'm the head of developer relations and marketing at Union AI. My background is actually in machine learning. I build production models for various industries, including real estate, and put them in production probably like 2015, 2016. We built large-scale deployments. I'm super excited that this topic is our topic today, and I'm really happy to welcome today a guest, which is Rolando Garcia. He and his co-authors wrote a paper about operationalizing machine learning, an interview study. They went out and spoke to various participants in the study to learn about how machine learning is being operationalized. Rolando is going to speak for about 30 minutes, 35 minutes today. After his conversation, we will invite a very exciting panel today of employees from various companies, including Lyft and others. And we will have a conversation about the pitfalls of operationalizing machine learning, the role of software, the role of team play, and most importantly, what to do to really get to the right level of velocity. And velocity is a term that you will hear in a little bit in more detail. Before I introduce the speaker, I would like to go over a few housekeeping notes today. First, this is a recorded session. It will be available on union.ai via YouTube. But you, of course, can also see it today on YouTube in a live stream. We'll also produce a transcribed version of this conversation as a blog post on union.ai. And if you have questions throughout the presentation, feel free to type them into the chat. The team will hand them over, and we will pick a selection and read through those questions during this session. Now I would like to introduce today's speaker, Rolando Garcia. Rolando is a Ph.D. candidate at UC Berkeley. And Rolando, please unmute yourself and introduce yourself and let us know what you found out in your study. The stage is yours.
I'm Rolando Garcia. I'm a sixth-year Ph.D. candidate at UC Berkeley, and I'm really excited to share with you our findings from our most recent interview study, where we spoke to ML engineers to understand how they operationalize machine learning. So a quick outline for the talk. This is, again, something that I will cover in 30 to 35 minutes. So I will be skipping through a few subsections. We will talk about software engineering, what's MLOps, DevOps for ML, what's the background here, discuss some of, I will spend a lot of time discussing the description or characteristics of the production ML workflow, what it is that the ML engineers that we spoke to spend their time on. And then I will also be talking about some practices and pain points, but this will be light and something that I will defer until the panel discussion. If you have some clarification questions, please feel free to ask. If you want deeper discussion questions, I think that's something that we can defer until the panel. So to motivate this, machine learning is something that we're finding increasingly in more and more places. So there's personalized medicine, healthcare, self-driving cars, and the list of fraud detection, the list is endless. And so what we wanted to understand was, who is a machine learning engineer? What kind of data worker are they? What's their specialty? So a machine learning engineer is going to be someone who might be dealing with TensorFlow plots. They might also be setting up RPC endpoints where they're deploying a model for low latency prediction serving. They'll be working with data silos, centralized schemas, features, Excel, and a broad set of different tools. So how much of this work can be done without formal ML and CS training? And how can we build relevant and useful tools for these machine learning engineers? So if we look at examples from textbooks in machine learning, or if we were to take undergraduate classes to learn how to do machine learning and how to deploy, the things that we would learn is that the first stage is data collection. There's sourcing, labeling, cleaning, and wrangling. Then from that collected data, we fit a model. Then we evaluate that model on, say, a held out data set, and provided that there's good accuracy and no overfitting, we deploy. There's some focus maybe on the evaluation and deployment part. And so when we're training the model, we see that the loss decreases over time. And then the validation starts to increase. That's indication of overfitting. We can pick a point in training when the validation is closest to the training loss, and we can choose whether to ship. We found that this assumption is too simplistic, and it's not representative of the work that ML engineers do. So this new wave of software engineering, which is a subset of DevOps, is the subset, is that is very hard to operationalize. So what about the naive textbook scenario might be incorrect? What might be some of the challenges? So in reality, it's never just once and done, right? It might be for a report, maybe you train a model and produce a plot. But in more realistic scenarios like fraud detection, it might be that people start adjusting to your new classifier. And so you need to account for this change in behavior. So the ML engineer is going to be continuously looping, and then the end user is going to be adapting. And so we're introducing people, and the people are adapting to one another. The data is going to change very frequently. The models are going to change in order to be able to keep up with changes in the distribution of the data. The customer needs are going to change. Business goals change, as well as teams change. So teams changing is like employee turnover. Employees come in and out of the company. How do you keep that context over time? So the ML engineer here is like acting almost like a ninja, keeping all of these different changes, managing all of this, and keeping control of complexity. So the ML engineer is someone who's going to be leveraging skills drawn from data science, data engineering, and software engineering. Specifically, they're going to be responsible for data cleaning or data preparation, feature engineering, which in our interview study comprises a large chunk of what drives innovation in ML engineering. There's going to be experimentation with the model as well as with the data, staging deployment, which involves, incrementally releasing a model, watching its behavior with real users, and then as the trust increases, giving it access to more and more flow of the traffic. Monitoring and debugging are an important part, again, just because we don't really have a very analytic understanding of machine learning, so its success or failure is defined by its behavior and its interaction with customers. So how do people put and keep ML models in production? We went out into the field and we spoke to 18 ML engineers, 4 of who were ML engineer managers from companies that varied in sizes, from small startups in Silicon Valley to large international corporations in sectors as varied as autonomous vehicles, retail, ads. So some of the more classical machine learning examples that might do well with like a linear classifier versus the more state-of-the-art examples that require deep learning models and more sophisticated architecture and infrastructure. So we're going to step next into the production ML workflow. The first step, data collection. A correction that we want to make from maybe the earlier scenario is an emphasis on experimentation, not so much model training. And this is because a lot of the experimentation is going to be coming in from the data or the models, and not only specifically the models. Evaluation and deployment is going to focus on change. So dynamic validation data sets are a delta here. Specifically, if you're assuming that the training data is changing over time, it's reasonable to also assume that the evaluation data needs to keep up with that change. And then finally, monitoring and response is something that happens continuously and at every stage. So you're monitoring the experiments, you're monitoring the data collection, you're monitoring the evaluation and the deployment and so on. So the practices that manage these workflows, the activities that the ML engineers are performing are as follows. The first takeaway, and this involves the data preparation and data collection step, is a lesson that iterating on the data produces a lot of value. Participant 11 says that they're going to start with a fixed model because it means faster iterations. That means not changing the model. And often, like most of the time empirically, it's going to be something in our data that we can use to kind of push the boundary. Obviously, it's not dogmatic. We will never touch the model, but it shouldn't be our first move. The emphasis again here is when you're iterating in machine learning, you can get a lot of value from iterating on the data, whether that's feature engineering or some other data transformation. Participant 11 further says that they really think it's important to bridge the gap between what's often a subject matter expert in one room annotating and then handing things over the wire to data scientists, as seen where you have no communication. So this relates to the importance of collaboration in data-intensive workflows, which is something that's well documented in the literature. P17 also says that they look for features from data scientists who have ideas of the things that are correlated with what I'm trying to predict. So maybe addressing some of the incorrect assumptions that we brought into this study is that the attention should be less on iterating merely on models and more on iterating on data. Rather than developing machine learning in silos, which is quite typical in academic settings, and then passing the model or handing it over to someone else, which is actually how mistakes happen. The tips that we learned was to involve other stakeholders in discussions. And so if we are people who work with experimentation, being involved in some of the data collection, and then also being involved in some of the product side discussions that are going to influence the decisions that we make for modeling. And rather than maximizing the number of models that make it to production, which I think in some academic circles is a priority, we think that the maximization of the iteration speed or the development velocity, the number of alternatives that you're able to explore in a finite amount of time, is going to be key. So revisiting the ML lifecycle, the emphasis here will be on dynamic validation data sets. P8 tells us about the dynamic validation sets. Every failed prediction gets into the same queue, and 3 of us sit down once a week and go through the queue. Then our analysts collect more similar data. And so it's very difficult for ML engineers to anticipate the kinds of failures that the model will have. And often models fail to different degrees with different subpopulations. So in self-driving cars, you might imagine that a model that's trained in San Francisco might never have seen snow. And so in those cases, when it's driving out in a different setting, it might have different errors. So debugging this, finding the error cases, and then integrating them into evaluation sets for future ML engineers to validate will be crucial. P15 tells us about the importance of multi-stage evaluation. They spend a long time very slowly ramping up the model to very small percentages of traffic and watching what happens. When there was a failure mode, a product person would ping us and say, hey, this was kind of weird. Should we create a rule around this? Suggested text to filter this out. So we saw that filters, rule-based or logical checks comprise an important part of AI systems. So it's true that there's this stochastic model underneath making predictions, but then there's also this layer of human readable and interpretable filters that makes sure that some common sense behavior is guaranteed for the user. On the importance of evaluation, again, if you're going maybe to Kaggle or Udacity or one of these online courses, you see ROC curves, F1 scores. These are all ML metrics, right? Accuracy, but they don't always translate into value for the customer or some meaningful product metric. So P16 says that the first task will be to figure out what the customers are actually interested in, or what the metric that they care about. P17 says that if they can get statistically significant improvements of people subscribing to a product, then they can fully deploy. So it's not just finding a model that has higher accuracy, it's making sure that that higher accuracy in fact leads to more subscribers. So managing this change, the static holdout sets that almost like k-fold cross-validation where you like take out some data from the training and then evaluate, that's not modern, that's not current practice. The evaluation data needs to keep up with the training data. So as the training data changes, as the distribution shifts, you need to make sure that the evaluation data is keeping up with that. Global metrics for machine learning are insufficient. Instead, it's necessary to slice and dice to check the performance on particular subpopulations, and then also to collect. It might be that the reason why the self-driving car is making mistakes in icy roads is because it doesn't have that experience. It's not enough to just detect that. You might also need to schedule some jobs to collect that additional data to improve performance. And ML metrics are insufficient. It's necessary to make sure that the metrics align with product metrics. And as one respondent said, that it's important that they measure success and are held to account by the same standards as everyone else in the company, which might be through like, revenue, income, or some other metric. Throughout the talk, you've heard me talk about filters or rule-based heuristics. This is kind of like human-in-the-loop practices that make sure that everything runs smoothly. So something that was interesting, very interesting to my co-author Shreya, is that if you're trying to do research in ML engineering, I think one really big open problem in academia is the data distribution shift. So we know that you can deploy a model, and then maybe in a year, there's going to be totally different trends. Try to think about the models that were deployed before COVID, and then COVID happened. So it's like hospitals maybe weren't scheduling virtual machines, and then all of a sudden they need to schedule virtual machines. So that's an example of distribution shift. And there's an abundance of academic papers in this space that try to build models that are robust to this change. And so it's very complicated, and we were going to ask the participants, like, how do you manage this change? And the answer was that they actually have a way of circumventing that problem through frequent retraining of models. So P14 says, why did we start training daily? As far as I'm aware, we wanted to start simple. We could just have a single batch job that processes new data, and we wouldn't need to worry about separate retraining schedules. You don't really need to worry about it if your model has gone stale, if you're retraining it every day. So if you have a model that was trained on data before COVID that services people before 2019, and then a model that gets retrained afterward, that model will be trained on that new distribution of data. And so now we're talking about, there's continuing this example, there's the model before COVID, there's a model after COVID. You always have the possibility of rolling something back. I think this was something that I myself was worried about. Like, if you're putting out models into the world that are making predictions and interfacing with users, what if you put out a really bad model that makes a terrible mistake? In my head, it's like, well, how are you going to keep a model from like an airplane from like crashing, right? And then in reality, the MLEs found a way to circumvent this problem through a simple rollback. There was already a model there to begin with before you deployed the new one. And so if there's something that goes critically wrong, you're always able to roll back. P18 says that it's important to keep some model up and running, even if we switch to a less economic model and have to just cut the losses. So this relates to the performance latency trade-off, which is, again, you might have a smaller model that makes a quicker prediction, but it's not as reliable. There's going to be different applications. So the application is going to demand, like, is latency more important? Is accuracy more important? MLEs have to navigate this decision space. The validation of inputs and outputs is going to be key. The data gets validated not only as it comes into the model, but also the predictions that the model performs. So then clarifying some of the myths that or initial assumptions that we brought into the study. Rather than building models robust to data distribution, the simpler solution is just to retrain frequently. So periodic retraining. This is something that was very typical. Every one of the MLEs that we spoke to retrains on a regular cadence. They always serve the latest model predictions. Well, no, not always. It's like a one-shot deployment case. That's more of an anti-pattern. Instead, it's better to maintain simple models and heuristics for rollback. And rather than validating just the outputs, validating inputs and outputs, and having on-call rotations and service level agreements to make sure that the model is performing as required. So the three virtues, so this is more for sparking discussion. The three V's of MLOps are velocity, early validation, and versioning. So these are themes that we saw recur throughout the transcripts. Velocity, it's about the rate of iteration. High iteration speed is the name of the game. The more alternatives you can explore, the better. There is a caveat to that, obviously. I know that a colleague of mine, Doris Shin, with Aditya Parameswaran, recently released an interview study on AutoML, and they found that its popularity had somewhat declined. And I think the reason why that is if you're running a bunch of experiments in parallel, but you're not really observing the outputs, you're not really learning from the previous experiments. It might also be a lot of context to keep in your head. Instead, the ML engineers told us that they preferred to have a more limited number of experiments that they were continuously running, and then they would have hypotheses about, well, maybe, I need to change my weight decay, or maybe I need to change the learning rate, some hyperparameter. And then this kind of like theory-driven guided search or hill climbing resulted in better experiments. But there's, kind of a tension. The faster you move, the more versions you generate. So there's kind of a software engineering burden there. And then same with early validation. I think if you one way in which like velocity and early validation created a tension, ML engineers told us about the importance of everyone on the team evaluating similar models with the same script. And so they would have this central repository with like Jupyter Notebook evaluations. And what they saw was that people would fork that notebook, run their evaluations, change that notebook, but then they wouldn't merge those changes back. And so that's one of the reasons where like the simplicity and direct access can then kind of lead to version drift. So I think we go into some of the tensions and synergies between these three V's and how they help us understand the problems that the ML engineers face. But it's something that we can discuss later in the panel. So for pain points, I guess for anti-patterns, keeping GPUs warm is an expression that struck us from the interviews, which just means like running experiments for the sake of running experiments. Or, if you're working at a large company, they might have hundreds of really high-end GPUs, and people kind of feel like this obligation to keep the system saturated with experiments. And it's like, that's not necessarily productive. It's a caveat on velocity. And then people retrofitting explanations, someone said that the reason why people succeed is because they're smart about the experiments that they try, and they try a lot of experiments quickly. They might have, like Dropout. If you read the academic paper for Dropout, it sounds very much like they reasoned it from first principles. But I don't know, I'm kind of skeptical. I feel like it was more like you destroy the image and then, it generalizes. And then later afterward, you try to fit some explanation, right? Undocumented tribal knowledge was an issue. This relates again to employee turnover. So there was a case of someone setting minimum and maximum bounds for a column, and then issuing an alert if the column value was outside of those valid ranges. But then that employee left the company and a new employee came in, and then no one in the company knew how to interpret those bounds, and so they ended up getting rid of them. So dev prod environment mismatch was a problem that the MLEs highlighted. They also encountered problems with data leakage, Jupyter Notebook usage. People who have used Jupyter Notebooks might be familiar with some of the issues with reproducibility and version control. And then code reviews. Sometimes people said that there's bugs in in ML code that you're not going to be able to catch through statistical techniques just because they're going to have such a small effect on ML metrics. I think in this case, the self-driving car, they copied the logic for like the left lane versus the right lane. And well, one's a passing lane, the other one's a driving lane, and so they have different logic. And the model was performing relatively well, so it's not an error that they could have caught unless they were doing code reviews. So it's also important to read the code, even if it's not changing as frequently as the data or the metadata. The ML engineers highlighted alert fatigue as an issue that came up. So if you trigger too many alerts, people will start ignoring them. Um, a sign of maturity that we saw with MLOps is that we're starting to see on-call rotations. So people who train models and deploy models will then also be responsible for them for like the course of a week or 2 weeks, and they have to open tickets and write reports on the performance. So there's definitely a lot more ownership with the models, as we saw. Taming the long tail of ML bugs. We tried to see maybe for like tool builders if there was some way that we could automatically maybe do like automatic bug finding on the model or the data. Like, is there some kind of classic failure scenario that we could fix? I think a common one was like setting random seeds in distributed training. So if you have multiple workers doing gradient descent on the data, they should scan the data in different orders. If they're scanning the data in the same order, then you're not really doing parallel training. So initializing random seeds was one of the few things that several people mentioned. But other than that, it's a very long tail. It's one of those errors where like maybe they encounter once in their career and they never see it again, but they waste a bunch of time fixing it. And so really what you have to do is just support this long tail of bugs and provide tooling that enables people to probe state in the model. So someone early in the interviews told us that something that might be helpful is almost like being able to probe data on a worker right before it goes into a model or right before it gets transformed. Like that might be useful. So yeah, the silent error from ML bugs, and then the paranoia in writing ML code and reviewing code. So this is, I think this was the same participant who told us about the lane changing problem. So for the MLOps stack, this is a way of managing complexity. People talked about, well, at the bottom, we understand there's the infrastructure. Are they running on Google Cloud, Vertex AI, SageMaker, something like that? Components, you have Docker, Kubernetes, this individual elements in the pipeline. People talked a lot about DAGs. So there's data pipelines, there's model training pipelines. And top level is you can imagine how you can, just like you call make on a make file, you can run these DAGs and then parameterize them. And so most of the change was limited to the run layer. And then it was like each deeper layer, people were changing things less and less frequently. So in this diagram, we're showing like the kinds of systems that people used across different layers at different stages. And so we see that for weights and biases and MLflow, like that's ways of managing metadata or hyperparameters from the run layer, very much in experimentation, evaluation, and deployment. And there's other systems, maybe like Airflow for DAG scheduling, Jupyter Notebooks, PyTorch, Hugging Face, TensorFlow were very common individual components for model training. And maybe to say like something that again keeps coming up is that there's someone who writes the PyTorch or the TensorFlow. Once that's written, then people don't have to revisit it and rewrite model training from scratch. Changes are incremental, and then again, limited to something along the lines of changing the hyperparameters rather than changing the architecture of the model. So we're working on this interview study. We've submitted to Kai, it's under review. There's other work that covers program slicing for notebooks, observability and machine learning pipelines, and then hindsight logging for model training, and then working with data bugs. So this other research that's going on in the lab. So yeah, it looks like we're about right on time. So I will open up the floor for the panel, Martin.